just like regular sign. So that means you have C1 equal to 1. Simple. Simplification like this was achieved by this dimensionless form. If you do not do the dimensionless form, this one will be complicated. All right? So you have C1. You need another boundary condition to identify C2. The second boundary from this picture would be at Z equal to L. But what do you know at the bottom of the beaker? Is CA equal to 0? Does it necessary 0? No. So this is not true. What is true? What is always true at Z equal to L? We know for one thing, A, the molecule of A, can never penetrate the bottom of the beaker, right? So that means the flux itself at Z equal to L is 0. It's essentially 0 because A can never penetrate the bottom of the flask of the beaker. If the Na is equal to 0, from here it means that dCA by dZ is equal to 0. Why? Because earlier we found that NaZ equal to minus dAc star dCA by dZ. Earlier we did find that. And therefore, from this boundary, it means that differentiation of Ca by dC equal to 0. From that, you can convert to dimensionless form of sine and gamma and solve for C2. All right? If you did that, you can solve for C1 and C2 and plug it back to the concentration profile, this equation. You can get the profile. As you can see, from there to here requires complicated mathematical rearrangement. So I'm not going through it. Okay? Any question? By the way, from the picture I just erased, you have bigger and A diffused into the liquid along the way it reacts. So if you stir it, at the end, if you leave the reaction to take place for a while and you stir it, what will be the concentration that you got in the beaker after stirring? From this equation, it tells you that Ca is a function of Z, right? If you stir it, that means you you did something so that the concentration everywhere will be uniform. That concentration after the stirring would approach average concentration, right? So stirring would give you average concentration. It is equal to integration of Ca with respect to Z from Z equal to 0 to Z equal to L. Okay? So this one is mathematics, but in physical meaning, it means that you take a beaker and stir it. The result, you get this average concentration.
You have to divide equally by L or something.
Oh, yes, of course. Divided by dz 0 to L. All right, the last example for chapter 18 is this. Suppose you have a solid wall with height L, okay? Over this wall, you flow some liquid to form very thin film of liquid B on the surface of the wall itself. Okay? The thickness of this film is delta. And suppose delta here is very small. That means you have thin layer of liquid B coating on the wall surface. So you have a wet wall. Outside the wall, out here you have gas. Gas A. Okay? You can have A in B or A in any species. But only A can dissolve into liquid here. So molecule of A dissolve into liquid. In other words, it means that A is absorbed by liquid B. You're taking unit 2, right? And you are, I think you know something about absorber. Did you take an examination regarding absorption? Yes, absorbing column. It is indeed absorber. Imagine this one is a packing materials. And you have liquid which would act as an absorbing or scrubber. Liquid would coat it as a thin layer on the packing materials. And then the gas that you want to absorb dissolve into liquid layer. All right. So suppose the concentration of the liquid, concentration of A in the liquid layer is ZA0. That means concentration everywhere would be ZA0. Okay? If the liquid that is coated or supplied over this packing material is pure B, that means up here, up here, B has not exposed to A yet. So concentration of A at the top part of the wall will be constant, equal to 0. But once gas A is exposed to liquid B, concentration up here supposed to jump up to Ca0 and then decrease down very, very fast. That means this area has not exposed to A yet. Only on the surface that A reached dissolve into B. Once the liquid flow downward, it would have longer residence time for contact with A. So therefore, A would dissolve into liquid more and more. Right? Down here, you get something like this. Because A would have more chance to swim into this liquid. So as every time we consider a problem, usually we will put our axis in the same direction as the flux of our interest species. If we are interested in the movement of species A, our axis is supposed to go in the direction of A. But in this case, obviously, A would go in this direction. So let's call this one X axis. But in this particular problem, A moves in two directions. In X direction, because of the difference in concentration. Around the surface here, concentration of A is high. I'm talking about concentration of A in the liquid is high. Around the wall here, concentration of A in the liquid is lower. So therefore, you have driving force for diffusion in X direction. On the other hand, when A is dissolved into liquid, the liquid itself flowing downward. So A is swept with the current of liquid B. So A is supposed to go downward as well. Let's call this downward direction to be Z. So in this particular problem, you have two directions of mass transport. If you look at the wall itself, you look at the liquid itself, if you disregard dissolving of A into liquid, if liquid here is pure B, okay, you can find velocity profile. Can you? I hope you still remember how to find velocity profile. The velocity profile should look like this, right? And velocity along Z direction would be Vc maximum 1 minus x over delta squared. Remember, this velocity profile is achieved by doing momentum balance, assuming that liquid is one single component, right? When we did learn about velocity profile of momentum balance, we treat all the species in our system to be single species. So if you assume that dissolving of A into liquid B does not change viscosity of the system much, or does not change density of the liquid. Liquid density and viscosity can be treated or assumed to be constant along the direction Z. Then you still can get this velocity profile. Okay? Then that means you will try or conduct momentum balance first, because you know that mass transfer does not affect momentum transport much. Once you get velocity profile, then you can step on by doing mass balance. So in this particular case, what does the shell mass balance look like?